Вот он появится. У них появится. Ну вот. Все.
Good morning, everybody. We start lecture on biophysics, and the title of the lecture you can see here. It is lecture under number 5. It is biophysics analysis and modeling of human tissues, electric properties, and effects of electromagnetic factors action. So, and what are the goals of our today's lecture? It is the number 1, specification of electromagnetic factors and quantification of their action on matter for analysis and modeling of factors, action, effects in human tissues. So look, what is this? We should recognize what are electromagnetic factors and what are the quantities of these factors influence on the matter. This is required to analyze and to model the factors, action, effects in human tissues. And the goal under number 2, it is the quantification of human tissues, electric properties, and processes to develop evidence base for physics, diagnosis, and treatment methods correct choice. So, and the objectives of our lecture today are these: electrodynamics parameters and basic laws nomenclature review, and electromagnetic factors identification. After this, we will consider applications of electromagnetic factors in medicine, and after that, we recognize, I'm going to represent you physics methods of registration of electric processes in human structures. It won't be too long list of that physics methods. We stop and recognize the one from this, the registration of electrical activity of the cardiac muscle. So let's start from this as introduction. Actually, it is the review of electrodynamics parameters and basic laws nomenclature, and electromagnetic factors matter influence. So let's start from this point of our lecture. Okay, electrodynamics actually, it is the section of the physics, and it generalizes electricity and magnetism. Electricity is the set of physics phenomena associated with the presence and flow of electric charges, and magnetism occurs due to electric currents. Electrodynamics is physics section that deals with rapidly changing electric and magnetic fields. Look here, and you can recognize that basic, that is actually under number 1 at this as electrodynamic dynamics section of the physics. What is this actually? It is the electric charge. It is very interesting physics phenomenon. Actually, it is the property. What is the physics phenomenon? It is the property of the real material object to produce, to develop into its vicinity, into the space surrounding it, the one more kind of the matter. And this kind of the matter is the electric field. When we talk about electric charge, we first of all understand that the elementary charge is required to make the other real material objects to be charged. And the elementary electric charge is actually the electron. What is the meaning of the elementary charge? It is the charge that can't be separated, can't be broken down into the smaller of magnitude charges. So, and this is just the electron orbiting into the atoms of the substances. And this charge is prescribed with the negative sign of the charge. And the positive one may be found at the nucleus of the atoms of the atom of the substance, and it prescribed with the positive plus sign. And look here, you can see this magnitude of the elementary charge. It is of 1.602 times 10 to the power minus 19 coulomb. So, and the macro unit of charge is the coulomb, equals to charge of this number of the electrons or the protons. And you know this as unlike charges attract and like charges repel. And this force is the force of interaction. Would it be attraction? Would it be repelling? Doesn't matter. The force is developed of interaction between the charges. The next, let's consider that vicinity surrounding the electric charge. As it was said already, the electric field is developed, and how this electric field may be recognized, maybe revealed. So by the placement of the probe charge into the space of this electric field, and the force is developed to subject that probe charge. And the magnitude of the force equals to the strength of electric field times the magnitude of the probe charge. And look, the electric field is identified, is quantified by the vector, that equals to the ratio of the force that is developed by electric field over the probe charge magnitude. So, and these vectors is the electric field lines. Okay, and this is one more diagram showing you, representing you the situation of the single electric charge. It is the circle with a plus inside and Q capital nearby, showing the electric charge that is single and that is at particular place of the space, and into its vicinity, into the surrounding space, this charge develops electric field. And these lines just the lines of electric field that shows the direction of the force that subjects the positive charge that is placed at the electric field. But at this situation, we can look from one more point of view, that two charges, Q capital and Q small, both are interacting with one another. And the potential energy of two charges, Q small and Q capital, separated by a distance, may be represented by this equation, by this analytical formula. So that is why we can look at electric field from one more point of view. I said already that it is the kind of matter. So the distinguishing features of any kind of matter are the two. First of all, if it is the material object, we can say about substance carried by that material object. And the energy this material object can possess. But when we say about one more kind of the matter, about the field, as in this case electric field, we should say about the only one, its intrinsic property to carry energy. So that is why we should describe the energy characteristic to the electric field. And look, it is just electric field potential. And this electric field potential as energy characteristic can be calculated as the potential energy this electric field provides to the probe charge over the magnitude of this probe charge. This is measured in volts. So, and look, this is just that opportunity to recognize physics approach to analyze, to describe processes and the properties of the objects. Would it be matter? Would it be field? Would it be material object? Something like this. What do I mean? If we talk about different electric field, how we can differ these two fields? Any word is required to say, to describe how the fields differ from one another. But this as potentials difference reveals that different or proves that electric fields are different. So, and then when probe charge will move into electric field, would it be the force developed by the field? Would it be external force that is applied to the probe charge, subjecting this charge against the electric field? In all cases of the motion arrangement, we should support by the amount of work that should be done to move that or another material object. And the work done by or against electric field by external force equals to this product of the magnitude of the probe charge and potentials difference at the points between which this charge is moved. So look, and then the single charge develops into its vicinity, into the surrounding space, not of too large strengths. But if the collection of charges will be provided into the space, electric field might be become of the strength that is noticeable. And how this may be arranged, this collection of the electrical charges. Look here, you can see here the two flat plates that are connected to the battery, and these flat metal plates are separated by the space might be filled with the dielectric. That material that doesn't conduct electric charges, doesn't conduct the electric current. So, and these charges that go from the battery are stored at the surfaces of these two plates. And as any electric charges, would it be single, would it be collected? These two collections of positive and negative electric charges develop into this space separating these two plates electric field. And now you can see that lines of electric field developed into the separation of the plates are of the same directions and are of the same density into the space of the separation. So that is why we talk now about uniform electric field. And as any electric field, this field stores, carries energy, and energy may be calculated using these analytical equations. And look, one more time, let me pay your attention that when we talk about property in physics, this property is quantified. In particular, in this case, look, we talk about the about the property to store electric charges on the surface of the material objects that are flat plates in this particular case. So consequently, physics gives us the opportunity to quantify that property. And this is just the capacitance, this property to store electric charges on the surface of the material objects is termed as the capacitance. And in this case, as the capacitance, it is just the term for the physics parameter. This capacitance may be calculated by that means. The amount of charge, the magnitude of charge that is stored over the potentials difference at the plates. So look, the energy may be stored in form of electric field energy. So this we will require to recognize how this may be implemented in medicine, in medical practice. The next, all materials may be classified, separated into two types, insulators and conductors. A material with internal free charges is defined as electrical conductor. Materials with the free charges inside. The first type conductors are the metals, and the free charges we can find there are electrons. The second conductors type are electrolytes, and the free charges we can find there are ions, the fragments of the atoms. And an electrical insulator is a material whose internal electric charges don't flow freely. So there is no free electric charges inside the insulators. So, and look, when we talk about the second type of the conductors, we can take as an example the water solution the water solution, in this particular case, the simplest situation may be considered. The table salt is placed into the water, and the water molecules break down the sodium chloride molecule into two components, into positive sodium ion and into negatively charged chlorine ion. So, and by that means, solutions become to be conductors with the ions as with the free charges that can be arranged into the directing motion. Okay, and look here. Let's consider a more detailed that phenomenon as electric current. It is the directing motion of free electric charges. In particular, in this example of the simplest cylindrical conductor, you can see the flow of the free electric charges. So, and look, this phenomenon is termed, this process is termed as electric current. At the same time, electric current is the term for the physics parameter measuring that process. And this is just the original definition of electric current as the parameter. Parameter as the measure of that phenomenon that is of the same name as electric current. So look, what is this? It is the total charge carried through the cross section of the conductor within time of the observation of the electric current divided by the time of the observation. So that is why the electric current measuring this process is the charge crossing the cross section of the conductor per unit time. And look, what should be mentioned else? This is just the influence of the material to conduct free charges. It is understandable that charges meet other structures of the material the conductor consists of. So, and this meeting may be considered as the collisions between free charges and other constituents of the conductor. So consequently, this may be referred as the resistance to the flow, to the directing motion of the free particles that carry electric charges. So, and this is referred to the resistance, and in the simplest case of the conductor with the cross-section area of the same magnitude along its length, the resistance of the conductor may be calculated. And one more, what is the reason, what is condition for electric charges that are free to be arranged into the only one preferential direction of the motion. And this condition is the potentials difference at the opposite ends of the conductor. And from the end of higher potential, electric charges are moving to the end with the lower potential. So, and this three: electric current, resistance, and condition for the electric current as the potentials difference or voltage are related by the Ohm's law. Electric current is directly proportional to the potential's difference to voltage applied to the conductor and inversely proportional to the conductor's resistance. And look, when we talk about physics, you and me as well keep in our minds why, what for do we need that physics basics? We need this to model, to quantify the properties and processes can be observed at the human body. The human body is actually the object of your interest as the future specialists, as physicians. So that is why let me pay your attention to the specificity of the electric current when it goes through the conductor of the second type. And what is this second type of the conductor? These are electrolyte. This is the solution, in particular in water, of the salts and bases that water breaks down into ions. And here you can see these positive and negative ions because each salt or base molecule is broken down into two kinds of the ions of the same charges, positive and negative. And if this solution is placed into electric field that is arranged, that is developed, for example, by these two electrodes, flat electrodes connected to the battery. Electric field is developed between the plates. We can say about the development of the drag force from electric field applied to the ions. And this depends on the strength of electric field developed. So, but as in the case of the metal, the ions meet the resistance of that solution. And this resistance is represented by the Stokes force and may be expressed by Stokes law. And you can see what is the reason, what is that caused that resistance. Look here, the viscosity of the liquid. This is the reason of the solution to influence, to resist the flow of the free charges as ions in this particular case. And look, the electric field may be chosen of proper strength to balance this Stokes force, and after this, the flow of the charges, the current of the developed by these charges as ions starts to be stationary. This means that velocity, independently that this is in progress, but the velocity would be maintained constant of this magnitude, And look, it is no different situation that was considered already regarding the metal conductor. So we can say about the electric current caused by this voltage applied and influencing by this resistance of the conductor. One more time, we use the formula to represent, to calculate the resistance of this conductor. In this particular case, the cross-section area of the conductor is the area of the plate, and the length of the conductor here is the distance between the plates where solution is placed into. So, and after that, we substitute this symbol by its by the equation to calculate it, and look, this resistivity of the conductor 1 divided by resistivity becomes conductivity of the solution, and this ratio of the voltage applied over the distance between the electrodes becomes the strength of electric field. And look, one more new parameter may be utilized. It is the density of the current. The electric current that crosses the unit of the cross section of the conductor. And after this, you can express the Ohm's law for electrolytes in this form. It is the convenient form for the electrolytes. Ohm's law. And look, we should take in account that this electric current into electrolytes are developed not only by the one kind of the free charges, but by two kinds of the free charges, positive and negative. So consequently, we could we should summarize these two positive and negative electric currents, and obtain this formula for the electric current density into the electrolyte. And look here, the resistance of the electrolyte is inversely proportional to the volume of the solution, to the so the more solvent, the less resistance of the electrolyte. And it is understandable from the very beginning that the blood or muscles, skeletal muscles in particular, into the human's body, carrying much enough liquids as solvent, are a very good conductor relatively with respect to that as fats and bones. So the tissues with the much enough solvent is the better conductor than that of the lack solvent. And look, one more, electric dipole. This phenomenon we will need to model the processes into the human body. What it is, electric dipole? It is the combination of two electric charges. These two are of the same magnitudes, and that are but of the opposite signs that are separated by distance. So, and the characteristic of the electric dipole is the electric dipole moment. It is, first of all, the vector directing from negative to positive charge, and also this vector magnitude equals to the product of the magnitude of the charge and the distance of the separation. And look here, this diagram shows electric field of the dipole. And you can see one more time that fields lines are of different densities into the space. So consequently, we can talk one more time about the non-uniform electric field and how this may be revealed, that non-uniform electric field. Very simple. You know already this. We put two electrodes into 2 points of electric field, and potential's difference will be measured. It will be done by, for example, voltmeter, galvanometer, something like this. But it is very interesting phenomenon. Let me pay your attention. And just this is we can find at the human's body. Look, independently that electrodes that are placed at these 2 points won't be displaced, the potentials difference that they are measuring will change if the dipole electric dipole moment will change its position into this space. Because look here, the potential difference, the voltage measured, depends on the relative position of the vector of the electric dipole moment and the line connecting these 2 electrodes. So if this as the direction of the electric dipole moment changes its position into the space, the voltage becomes different. The voltage becomes different. The next, if this of importance to recognize the influence of the electromagnetic factors of the human's body tissue. Look, an external electric field produces 2 forces if electric dipole is placed into it. When we talk about electrolytes, when we talk about metal conductors, we recognized the subjection, the forcement of electric field and arrangement, the motion of free electric charges. But the situation when electric dipole is placed into electric field is absolutely different. These charges are linked with one another. They are not separated. They are not free. So consequently, but nevertheless, to be free or not to be free, electric charges are forced by external electric field. But in the case of the electric dipole, the forcement is of 2 kinds. The force is developed to subject the positive charge, and the force is developed by electric field to subject the negative charge. So that is why we can say about pair of forces. The pair of forces. So, and this pair you can remember from the mechanics that the pair of forces develops the torque, and this is just the measure of the ability by that 2 forces to rotate. In this particular case, this rotation of the electric dipole will lead to orientation of the electric dipole along the electric field line. So, and look, an external electric field, by that means we can say, does work under electric dipole, and the magnitude, the amount of this work may be calculated by that means. So look, the work done, it is the process of the transformation of energy. Electric field energy is transformed into the extra energy of electric dipole. So electric field provides the energy to electric dipole when by that orientation process. So would it be electric charges that are free? Electric field transforms its energy into the electric current energy. This is just the kinetic energy of the motion of electric charges that are free. Would it be electrolyte or would it be a metal conductor? Okay, and look, where we can find that electric dipoles, in particular in human body. Look here, we know that some of the molecules that are organic molecules are not broken down by the water into the ions. They continue to be electrically neutral molecules. And in some molecules, the internal electric charges developing electrically neutral whole molecule are separated, are located at opposite ends of the molecule. And such kind of the electrically neutral molecule is termed, is referred as polar molecule. Polar molecule, so of that separated in it's not quite correct to say that these electric charges are separated. These are located at opposite ends. And look, and by that means that molecule may be considered, may be modeled by this physics model as electric dipole. So to be placed into external electric field, the situation will be the same as with the single electric dipole. Electric field, external electric field, does work under the molecules and orientate the molecules along the lines of electric field. So, and we can find one more kind of the organic molecules that are not polar, that molecules with mirror symmetry, like oxygen, for example, have no permanent dipole moments. They are not polar molecules. But when these molecules are placed into the external electric field, first of all, under the force of electric field, electric charges into this kind of molecules are located at the opposite ends of the molecule. The molecules are polarized. So, and after them, it is the second stage of the electric field influence that substance. One more time, this electric dipoles developed are orientated by external field. So look, now we talk about abstract substance, but you should keep in your mind the organic molecules are present in the human's body. And now you should recognize that influence of electrical at least factor as electric field the human's tissue. So the human's tissue. And the next we should recognize as the behavior of the dipoles into electric field. We talk about the uniform stationary electric field, but look here, the alternating electric field is illustrated here. What is the alternating electric field? This field is of change of electric force. It develops with time. And this electric force or polarity of the electrodes might change with these 40 megahertz frequency. And look, at one half of the period, it will be one orientation of the electric dipole. At the second half of the period, the orientation of dipole will change to the opposite. So that is why we can say that at the alternating electric field, electric dipoles start to rotate with the same frequency as the change of the polarity of the electrodes, as the change of the electric field frequency. So, and look, this change of the orientation means not means, but may be considered, and it is the extra motion of the electric dipoles. And these may be considered as the transformation of the electric field energy into the extra kinetic energy of motion of electric dipole. And when we talk about the kinetic energy of motion of the structures of the matter, this reveals as the rise of the temperature. So that is why, let me pay attention, and this is the implemented just in medical practice, that alternating electric field can heat the substances, in particular humans' body tissues. And when we talk about free charges, alternating electric field sets the free charges into the oscillations that free charges, and these will lead to the heating, and the alternating electric field can heat dielectrics as well. And the mechanism, the physics of this is just of the rotation of the electric dipoles in clockwise and anti-clockwise directions. And the magnetic field. Magnetic field is one more form of the existence of the matter, and it is the reason to develop electric field, magnetic field, excuse me, is the electric current. Electric current in its vicinity would be electric current in wire, would it be the electric current developed by the molecules, structures of the matter. So as in this bar magnet, the magnetic field is developed by the moving electric charges. Stationary electric charges develop electric field, and the moving electric charges that develop electric currents moving at the one preferential direction, that charges develop a magnetic field. Magnetic field is recognized, is revealed by the forcement of the electric charge, a free electric charge, that is placed into the magnetic field. And that magnetic field force on the free charge that moves with particular velocity may be calculated by that means. Magnetic force on magnitude perpendicular to the both vector of the velocity and vector of the magnetic field. So, and look, let me pay attention to this as any kind of matter. Would it be electric field? Would it be magnetic field? The magnetic field carries energy that depends on the electric current developing that magnetic field. So, and you can see this characteristic as inductance of the magnetic field. This is same as the strength of electric field. It determines the force developed on the free charge when it is placed into a magnetic field. So electric field stores energy, magnetic field stores energy. So, and look, magnetic field to be produced, to be developed by electric current influences subjects electric currents as well. We talk about the force that is developed on the free charge placed into the magnetic field. So, doesn't matter if the wire carrying current would be placed into the magnetic field, this wire would be subjected by the magnetic field. And look, when we talk about electric charge, we can say about the development of the electric field. When we talk about the moving electric charge, we talk about the development of the magnetic field. And look at this situation, at this example. Imagine to yourself that free electric charge that is oscillating, that is in up and down motion, for example. And what does this mean? This means that electric charge as itself develops electric field, but this is not stationary, it is changing. And this change of the vector of the electric field in direction and magnitude is of the same frequency as the oscillation frequency of the electric charge. And at the moment the charge starts to move, this charge becomes to be electric current, and electric current produces magnetic field. And this kind of the matter, magnetic field, would oscillate with the same frequency as the oscillation of electric current. So consequently, we can say about the producing of that combination of electric and magnetic field. Electric and magnetic fields are linked in continuous mutual transformation, and represent electromagnetic field phenomenon. Look here, the change in electric field produces change in magnetic field and vice versa. So, and this combination is self without to be carried, propagating into the space with this velocity, that is into vacuum equals to, 3 times 10 to the power 8 meter per second. This combination is propagating, self-propagating into this space. But if it would be matter, it would be different velocity of the propagation. Because of the influence of the substance to motion of this combination of electric and magnetic field. So, and look, this influence of the substance, the velocity of propagation is expressed by that formula, These parameters as epsilon and mu are matter dielectric and magnetic permeability respectively. So, and look, one more point of view may be suggested on electromagnetic. By the way, let me pay your attention. Let me emphasize. Let me stress this as electric field and magnetic field. These are moving, self-propagating, but remember, these two are carrying energy. So consequently, we can say about electromagnetic energy that is self-propagating into the space, not to be carried. So, and this phenomenon, when energy going through this space, not to be carried by material objects, is termed, is referred as electromagnetic wave. Any phenomenon. You know now about the sound. What is the sound? It is the process of the propagation of the mechanical energy, but this energy is carried by the particles of the air, at least, but not at last. So consequently, we should separate these two kinds of the waves, but these processes are similar in their natures. These are the processes of the transmission of the energy of two kinds: mechanical energy that should be carried by material objects, and electromagnetic energy that is self-propagating and doesn't require carrier for its propagation. So, and look, one more point of view may be suggested to consider electromagnetic wave. So, and this is the Max Planck theory that represents that considers the electromagnetic wave as the flow of something like massless particles that are referred as photons. Each photon carry elementary portion of energy that is of magnitude. It is the Planck's constant, and this is the frequency of electromagnetic wave. What do we mean under the frequency of electromagnetic wave? It is just the frequency of the oscillation of the vectors of electric and magnetic fields. These two are same and equals to the frequency of the oscillation of the charge we consider. So of the source of this electromagnetic wave. So these two. And look, the transmitted energy would be dissipated due to any losses within the medium. And the power dissipated per unit volume in a non-magnetic uniform materials exposed to electromagnetic fields can be expressed. It is very important to recognize that these power dissipated per unit volume depends on the frequency, and so consequently the dissipation falls down and with the frequency. So more power is dissipated in material at higher frequencies. However, the wave attenuation factor is higher at higher frequencies, and therefore the penetration of the heating into the surface of material is lower at higher frequencies. So this is just at the core of the implementation of electromagnetic waves in medicine to heat the tissues, tissues. Frequency influences this process. And look, the penetration depth of electromagnetic wave is inversely proportional to the wave frequency. Dissipation is directly proportional, but the penetration depth is inversely proportional to the frequency and depends on the attenuation factor of the material. And this formula is just to calculate at what depth the intensity will change, or amplitude of electromagnetic wave will drop up to this part of its incident magnitude. So it is formula just for this. And look, these electromagnetic factors matter influence. We considered electric field, magnetic field, electric current, electromagnetic waves. And look, this stores energy. This is a formula for this. And look, this energy, when the material is placed into electric field, the energy of electric field is transformed into the internal energy as the heat. And the magnitude of the heat that is delivered by electric field may be calculated by that means. You can see that alternating field may be arranged, may be applied in particular to the human tissue, and independently. Would it be non-living object? Would it be living object? In both cases, electric field independently, would it be stationary or would it be alternating, the electric field converts its energy into the form of the thermal energy into the heat. Magnetic field, one more time, it stores energy of this magnitude, of this amount, and one more time, it produces, it converts its energy into thermal form, into the heat. And look, this energy as the heat depends on conductivity of the material, so and depends on the frequency and the strength and on the time of the exposure. So that is why, look, as I said, as I promised you to quantify the electromagnetic factors, now I've done my best for you. I quantified, I show you that quantification actually. It wasn't done by myself, it is understandable. So, but nevertheless, I illustrate that we put as the goal of our lecture. And look, the influence of that electromagnetic factors are quantified as well. This is the heating. Would it be tissue? Would it be other material? Doesn't matter. And electric current, one more time, produces heat in conductors. And what are that conductors? These are electrolytes into the human's body. So, and this heat may be calculated by this. It is understandable. This should be added with the time of the exposure of the application of the electric current. So, and look, electromagnetic waves. This is the combination of electric and magnetic fields, and these two transfer energy. These two transfer energy, and this energy dissipated. And this dissipation of energy depends on the frequency of electromagnetic wave. So this was done as quantification of electromagnetic factors. And look, electric properties of the human tissues, we talk about better conductors, the that are of higher conductivity. And now you can look and nothing, no word is required to characterize the tissues from physics point of view as good or bad conductors. Look here, muscle, conductivity of the muscle, and the blood, its conductivity. Why it is the largest? Because of the blood composition. It consists of 50% of the solvent, of the water. It will be better to say not on of the 50% of the water only, but actually conductivity of the blood is determined by the presence of just solution of non-organic molecules into the water. Water makes the ions from that non-organic bases and salts molecules. So that is why the blood consists of 50% of that electrolyte. So, and this determines its the highest conductivity with respect to other tissues. Muscle, in particular skeletal muscle, is of big enough amount of the solutions, so that is why it is at the second place of its conductivity. So, and look, the electric properties of human tissue at different frequencies. You can see that properties: conductivity, dielectric constant, and penetration depth. This is the standards. This is just the protocol for the physician to make his or her choice of that or another electromagnetic factor to implement it for the treatment of that or another kind of tissue, for that or another organ. So this is just quantification evidenced base to make correct choice of electromagnetic factor to take it, to implement, to apply it at medical practice. So, and look, diathermy is that treatment, diathermy. It is now medical language to talk about the processes implementing electromagnetic factors to treat the human's body. Look, electric power can be transformed into heat as required in the body tissues if the frequency of the current is high enough for its passage not to be accompanied by an excitation effect. This condition is found to be satisfied if currents with a frequency higher than 10 to the power 5 Hertz are applied, not lower is possible. The energy produced in the oscillator of high frequency medical heat producing devices is transferred to the site of treatment by the patient circuit. The oscillator receives its power from a direct voltage supply or an mains transformer. To avoid electric shocks, the oscillator supply voltage must not pass into the patient circuit. It is very important. And look here, you can see the classification, the types of the kinds of the thermal of the heating of the human tissues. Deep heat is produced when electromagnetic energy is converted into heat as it passes through the body tissues. Energy sources include high-frequency currents, it is short-wave diathermy, and electromagnetic radiation, microwave diathermy. So the temperature rise depends on the properties of the tissue, the specific heat, thermal conductivity, and the length of time that the heating modality is applied. And you can see that a magnetic field is the most effective to heat the muscle tissues because magnetic field induces the electric currents, and this is extra motion of the particles, and it is understandable the better conductor in better conductor the more heat is produced. Capacitive plates electric field is more preferential to treat the tissues that are rich with the fat kind of tissue. And microwave. Look, you can see this is of the same effectiveness for fat and muscles. So these are the classification. And look, more detailed and let me illustrate this. Excuse me, please. The areas treated selectively by the modalities. The application of the microwave radiation or of shortwave diathermy with capacitor plates at a frequency, you can see what is the frequency, can provide selective heat to deep subcutaneous tissues and superficial tissues. Heat is produced by the dipole effect. Look, it is illustrated here. Clockwise and anti-clockwise rotation of the dipoles and this extra motion produces heat of that amount, and this may be regulated by frequency and the exposure time, and by the strength of electric field. So, and look, a quantification of the electromagnetic factors influence the human tissues. The next, look here, it is just magnetic field, short wave diathermy with an induction coil applicator. How much heat will be supplied, the tissue will be supplied of that amount of heat. Quantification, it is of the choice of the doctor. The time exposure time, and the strength of the magnetic field, and the frequency. This depends on the conductivity. What is under the treatment? And the next, please, microwave overheats tissues by means of the microwave frequency electromagnetic fields. Microwaves are electromagnetic waves of the wavelengths, from 0.1 to 100 centimeters. They can be generated by a special generating lamp called a magnetron. So it is not different, the influence of the radiation. Remember that this radiation means the electromagnetic wave. And what it is? It is the combination of electric and magnetic field. So both are carrying energy, and this energy is transferred into the tissue, into the heat. Microwaves undergo reflection, dispersion, refraction, and diffraction on various complicated tissue structures. So look, about 50% of the microwave beam applied to the skin is reflected. The rest is absorbed by tissues at depth of only 6-8 centimeters. Remember that this wavelength corresponds to high frequency, and the penetration depends on frequency. So that is why this is such short distance. The microwaves can go through the skin. Microwaves cause an oscillation of ions in electrolytes and molecules in polarized dielectrics, and in this way create heat. The most overheated are tissues containing a lot of water, such as blood and muscles. Fat tissues containing little water is only slightly affected. So the shortwave diathermy is more preferential for the fat, as you know already. Okay, but contradiction should be taken in account. Contradication of the diathermy should be taken in account, please. And this is just the list of these. Look, metal implants or metal jewelry, cardiac pacemakers, and this list you should take in account when you are going to implement the diathermy to treat your patient. And look, it is the special iontophoresis procedure to deliver the chemical not by injection through the blood, because look, when the medical chemical is injected, it goes to the part of the body that should be treated, going through the whole organism. And this chemical is delivered not only for the suffering part of the body, but is delivered to all structures of the organism. And this may lead to the side effect, may not be harmful, but not good for the healthy structures. But this, as iontophoresis is the delivering of the chemical just to the suffering part of the human's body through the skin, And these two diagrams illustrate that procedure. It is a non-invasive method of propelling high concentration of a charged substance. The chemical should be represented by the ions in the solution. Normally, medication or bioreactive agent transdermally by a repulsive electromotive force using a small electrical charge. Approximately, electrical charge is of that density, 0.5 milliampere per centimeter squared. How is this technique working. Two electrodes are placed on the surface of the skin, and the medical chemical is represented by the ions are placed under the electrode of the opposite sign than the medication. And the electrodes, that is passive, is placed at the distance from the active electrode. Between these two electrodes, when the voltage is applied, the agents ions developing the current go inside the human body, crossing the skin. This is just the procedure of the delivering the medication by non-invasive method. And this provides the possibility to avoid a side effect by influence of this medication, the tissues that shouldn't be treated. And look, these are nowadays kinds of the iontophoresis modalities. Treatment for running injuries are very effective. Is best This iontophoresis is best suited for injured areas which are very near to the skin tissue. Tissue deep inside the body is too far for the effectively transported chemicals to effectively penetrate. So it is just look what are the drugs that are used for the iontophoresis, and what are the charges science of that medications, and this purpose condition to implement antiphoresis. So this is just for the to introduce the drug by non-invasive method. And look one more time, let me pay attention. This should be taken in account. Contradictions should be taken in account for the antiphoresis as well. The following are antiphoresis contraindications should be taken in account as well. And human body electric processes, physics aspects, and quantification. When we talk about human body tissues, let's start from the cells structural level. And we can find there the extracellular fluid and the intracellular fluid. And look independently on the location any fluid into the human body is the conductor of the second type. And look extracellular fluid is of these concentrations of the ions, and intracellular fluid is of these concentrations of the ions. And look, as any ion independently on its concentration develops electric field, and we can say about the resultant electric field that is developed outside the cell and that is developed inside the cell. So if we talk about the different concentration, as we can see, the concentrations of the ions are different inside the cell and outside the cell. So these should be suspected that electric fields that are resultant electric fields are different inside the cell and outside the cell. So please don't believe to this statement. It is the only suspicion. Look. This is the improvement of that statement. When two electrodes are placed into two electric field, suspected that these two are different, the potentials difference might be measured. And it is true, if we place electrode into the cell and out of the cell, this as minus 70 millivolts voltage is measured, proving this statement that electric fields are different inside and outside of the cell. So that is why these major ions is actually maybe considered as electrogenic ions. So, and after this, look, the Goldman-Hodgkin-Katz equation is just the equation, analytical formula to calculate that total, not total, resultant potentials difference between inside and outside of the cells electric fields. So, and when cell is at rest, so it is just the voltage calculation that was measured, and I talk about minus 70 millivolts for the nerve cell to be at rest. And look, let me demonstrate you this. Some of you know already this and have seen this. Nevertheless, it is the review of that you learned already supported by the tutors at the tutorials. Nevertheless, let me repeat one more time. The human nerve cell membrane electric model. We can consider the membrane as the resistor. It is number one model, and as the conductor, and these two are in series. And this is just the modeling of the electric properties of the biological structure as the cell membrane. And look, what is modeling for? For quantification of the properties of the biological objects. And you can see how good resistor is the membrane and poor enough capacitor a membrane is. So, and look, it is just the membrane that is under subjection, nerve cell membrane. It is the rest membrane potential or voltage that is measured. And when this, when the membrane will be subjected by chemical or electrical stimulus, the voltage measured will change with time. By that means, this is the change of the voltage measured at the membrane of the nerve cell with time when the membrane will be stimulated. And this start look at the threshold when the stimulus will be of threshold magnitude. Just after this, sodium channels open, and sodium will go into the nerve cell, changing the sign of the electric charge into the cell from negative to positive. And this is just depolarization of the nerve cell. After that, the potassium channels open as well, and they remove positive charge from the cell and restore negative charge. And this is the repolarization of the nerve cell. Hyperpolarization, because of the open of the potassium channels, and they remove more positive charges, and this negativity of the nerve cell drops up to this minus 90 millivolts. So it is an active potential, an action potential. So, and look, the human nerve cell membrane action potential is determined by the conductance of the membrane for the sodium and potassium ions. And this conductance is provided by the specialized selective sodium and potassium channels. And look, within a millisecond, the membrane potential changes from a negative to positive and back. You can see within the millisecond. So, and look, after this, the change of the potential will be conducted through the axon. But look, this is the saltatory conduction. The nerve impulse jumps from one node to another node. This is the specificity of the axon that is covered by myelin sheath, interrupted each 2 millimeter by 1 millimeter node. And finally, let's consider, we talk now about electrical processes. So, and this is just the example of how electric processes is just the major function of that specific organ as the cardiac muscle. Everything starts at this location of the pacemakers, developing the sinoatrial node, and after that, through the specialized cardiac muscle cells, the electric impulse goes through the atria first of all, and after that through AV node, atrioventricular node, goes to the ventricles to excite, I may say so, the working cells of the cardiac muscle that just contract and pump the blood from the ventricles into the circulatory systems, pulmonary and main. So, and you can see here, one more time, these are the quantification of electrical properties of these organ cells, different cells of the cardiac muscle. And conduction velocity, you can see where it is the most fast. It is just Purkinje fibers delivering the electric impulse to individual cardiac muscle cells to initiate their contraction. And actually, when we talk about the action potentials of the cardiac muscle cells, we can say about change of the voltage at that kinds of cells. Look, sinoatrial node generates this action potential. And look, you can see that platter. Why? Because the calcium is involved making the action potentials of the cardiac muscle different with respect to the nerve cells. And the resultant action potential that is developed of all cells within one cycle of the cardiac muscle is represented by this graph that is referred as electrocardiogram. So, and look, this electrocardiogram is the recording of the voltage that are measured by these three pair of electrodes, and these electrodes are placed on the surface of the human body, and this change of the voltage is different for the different pairs of the electrodes. And look, these are electrodes that are placed on the limbs, and each pair is the limb lead, and there are 3 bipolar leads. And to investigate more detailed, the chest leads are involved as well. And look, these parts or fragments of the electrocardiogram is marked by letters, and these each part reflects, gives information about the conduction of the excitation of electric impulse through particular part of the cardiac muscle. This P wave propagation of the excitation of electric impulse through the atria, Curies complex, it is the propagation of electrical activity, electric impulse through the ventricles, and this is just repolarization of the ventricles. And you can see how different are the voltages change with time when the voltages are measured by three pairs of the electrodes. And look, the shape of the electrocardiogram is analyzed, and experienced doctors' eyes can diagnose the condition of the cardiac muscle. Or nowadays it does more precise. It does more precise by the computer. So, and what is the summary? Physics models and methods quantify the parameters of the dynamics of the life processes of electric nature and allow objectively and evidence-based diagnosis of the human body. Example is the ECG. It is dynamics characteristic of the electrical nature process into the cardiac muscle. Physics models and methods objectively assess the degree of risks of exposure of external electromagnetic factors on the human body. And physics methods of exposure to electromagnetic factors with reasonably selected parameters have a therapeutic effect on the human body. It is just the heating. So, and finally, bibliography, physics in biology and medicine, and more long list you can find at the Moodle platform we developed for you to support your learning. Thank you for your attention. We finish. Have a good day.